This is a paper in ICML that is trying to sort of quantify different sort of locations that people shoot, and is doing that by using factorization methods, and more specifically non-negative matrix factorization. Now, a few introductory slides just to sort of set the stage for this. Of a Gaussian process that we're going to use here. Basically, whenever we have points in a continuous domain, either space or time, and these are normally distributed, we can say that they follow a Gaussian process. This is a typical probability function for the Gaussian distribution. Nothing new here, but then you can say this is how you symbolize that, this H mapping is a Gaussian process that is parameterized by a mean and this kernel, which is basically sort of the covariance matrix. And the kernel has to be a positive semi-definite matrix, right? So this is the only sort of constraint that you have in designing the Gaussian process. Now, you'll see in a few slides why we need to do that and why this makes sense. But in this particular work, it makes sense to use the squared exponential kernel because it's locally smooth, and so it tries to smoothen out different local sort of patterns and have a nice smooth curve in the space. Another thing you probably would need to sort of remember and jog your memory is the Poisson process. So if you have a point in space that is Poisson distributed, and usually that happens when we have counts of things. So imagine if you have counts of different shots taken from a particular point in the half court, then you can say that they're Poisson distributed, and this is how you parameterize that. You obviously need to have this lambda parameter for the Poisson process. And then you have different nice properties, such as the superposition theorem that says that if you have disjoint Poisson process on space, imagine different locations on the half court where people take shots from, then you can combine them by just adding up their parameters. And then this is going to be useful in understanding and interpreting the results later. Now, why do we use this? Is because there exists this doubly stochastic, and forgive me about the jargon, but this is going to make all sense in the next slide. A doubly stochastic process, this log Gaussian Cox process, that is a series of sort of stochasticity here. So we have this Z that is a Gaussian process, which parameterizes this lambda that further parameterizes a Poisson process. And basically, this is what the authors are using to fit to the shooting pattern of a particular player in the half court. So imagine that you have, let's say you discretize the court, and you have a different sort of x1 to xn. This follows a log Gaussian Cox process, which is parameterized this way. And the reason why they do it is because it models counts of shots, and they require this local smoothness that the Gaussian process with the squared exponential kernel ensures. Now let's get to the actual analysis of the data. But before we do that, this is the final thing that you probably may have more frequently seen, especially in KDD, is a non-negative matrix factorization, where you have, let's say, a matrix lambda, and you decompose it into different factors, a weights matrix and a basis matrix. So the basis matrix is telling you that these are the columns of the basis matrix are the fundamental latent patterns in your data set. And the weight matrix is telling you what are the linear combinations that you need to combine those patterns to create the columns in the lambda matrix. And we have the constraint that because lambda is usually non-negative, we also want W and B to be non-negative. And so there's different ways to solve that. One thing that makes sense to sort of pay attention here is that for arbitrary matrices, people usually use the Frobenius norm, which is basically the squared error of the differences between the data and the model. But in cases where we have discrete distributions, and more specifically counts of things, in which case here we have counts of shots taken, people they usually minimize the KL divergence of the data and the model, right? So then you see, I'll show you results from both minimizations. But in our case, perhaps the KL divergence makes more sense. Now here's the problem setting. We have for the 2012, 2013 seasons, we have data from where a shot was taken. And for most of the things I'm going to talk about, we mostly focus on the half court. So we care about the offensive part of the court, right? And so you'll see here, the raw counts is basically that, Steph Curry here took a shot from this particular location. And you see that Steph Curry mostly takes shots from all over the place, whereas LeBron takes shots closer to the basket. But here the problem is how you can understand different patterns on the offensive court and sort of categorize players on the way that they use those locations to shoot. All right, is this clear? This setting clear? All right. Now, what the authors do in this ICML paper is they have a 4-step process where the first thing they do is they make a player by grid matrix. So they discretize the court, and you have, let's say, V tiles. And for each player, they have the number of shots taken from each particular tile. So they aggregate all the shots taken for all the entire sort of duration of those 2 seasons. And this is how you create this sort of the count matrix. Now, then that's where all this doubly stochastic log-Gaussian Cox process is going to make sense. What they do is they don't take the raw counts, but they smoothen them out by using by fitting this LGCP process. And so what this does is it sort of smoothens out and takes care of noise that there might be in their raw counts. And so instead of using the X matrix, they use this lambda matrix, which is basically the fitted LGCP process on the counts on each tile, right? So this is basically transformation to make the data more smooth, right? After that, what they do is they do non-negative matrix factorization on this lambda matrix, which results, as we said, into the basis matrix that now is going to be particular patterns on the half court, and the weight matrix that says what is the combination of, let's say, LeBron James on shooting from the corner threes and shooting from the baseline. All right, so then we're going to use the combination of those 2 matrices to understand how each player behaves on the half court. And obviously there is a K parameter here, which is the rank of the NMF. And there's usually the best way to choose that is empirically, because people sort of do some trial and error and understand whether, the resulting patterns make sense. And I believe here what we have is K equals 6. But you obviously can do some sensitivity analysis and have some way of judging the quality of that. Now, I'm not going to go through these details, but basically the second step is how you fit this log Gaussian Cox process, and this is done by using maximum likelihood estimation. And this is the result, right? So let me unpack this for you. So these are the different bases. So each one of those is one column of the B matrix, where you just have, the B matrix is an unfolded set of tiles. So you just basically fold them back into the original half-court locations, and you plot, this is a heat map, right? So wherever the redder it is, the more intense, so the higher the values, right? So then the more intense the activity in this latent pattern. And you see here, for example, this is a pretty nice clear pattern of the corner threes. This is sort of the center threes. This is sort of the wing threes. And you have all sorts of things in the baseline. And all these patterns make sense. Now, these are the B matrix. And as I said, the W matrix gives you the weights of each player with respect to each particular shooting pattern. And so you see LeBron, for example, is mostly in this pattern here. You see the red values indicate the higher, sort of the high values in the weights. And you see, for example, LeBron is very dominant here, whereas, for example, Steph Curry is more on the southern threes and the corner threes, as well as, the 3-pointers, right? So here, this gives you an understanding, and a more formal understanding on the behavior of each player in the offensive court, right? And you can sort of look at this and try to see whether this matches intuition, and indeed, this is basically confirming what we sort of understand about these players. But this is an important thing to do because this helps us quantify things that we were not able to do beforehand. And you'll see some examples as I go through. Is this clear? All right. Now, just to sort of, as a sanity check, this is comparisons of different ways of modeling the problem. The first two rows are the whole sort of four-step procedure, where the first one is using the KL divergence. As I said, this is better when you model discrete processes of counts. The second one is the Frobenius norm. Now, the third one is if you forget about the second step, and you don't do the smoothing with the LGCP process, and you just do the NMF on the row counts. And the last one is if you do, instead of an NMF, you do PCA, principal component analysis. And so let me just highlight a few things for you. You'll see here that perhaps KL, those two are not too different. And so, the second step of the smoothing takes care of sort of the averaging out all the differences in the noise. And so you see that KL and Frobenius norm mostly give you nice smooth patterns. Now, if you forget about the smoothing, you get a little bit more raw and more noisy patterns. And so here, the third row, which is without doing the Laplacian process smoothing, even though sort of the patterns match most of the patterns you see in the first two rows, you might have some noise, right? So you don't have as clean-cut patterns as you would. Now, for PCA is one of the most popular decompositions. And one constraint is that the bases are orthogonal to each other. And there's no constraint on non-negativity. So because of that, and this is an artificial constraint with respect to our intuition, so it doesn't really match what we're expecting. And so if you plot the patterns, they won't make any sense. Because in order for the orthogonality to hold, you will have to have negative shots taken from this particular pattern, which makes the math work. It's optimal with respect to the squared error, but it doesn't really make intuition work. And so if we want to use this for interpretation purposes, we probably have a hard time understanding what it means. And so this is just to highlight the importance of the non-negativity constraints. All right? So another thing you'll notice is that we don't really need the orthogonality constraints by the PCA here, because most of the patterns happen naturally to be almost orthogonal to each other. So they happen to be distinct with each other. So you'll see here that we have a distinction of the corner threes and the other location for the three-pointers. And so naturally, as it happens from the data, this quasi-orthogonality emerges. And so we don't really need to go, the extra mile to make it fully orthogonal. And this works well in practice. All right? So this is all there is to this figure, just to understand different ways you could model the data. Now, why this is a useful thing to do? Because it can quantify shooting efficiency. And perhaps this is a good thing because instead of just counting how many shots on average a particular player is successful on, perhaps we want to see how many times this player is successful from shooting in that particular location, right? So how many times is the player efficient when they shoot from the corner threes or from the baseline? And because this is sort of trying to tease out different effects that might be sort of conflating when you just measure the average, right? So this is one neat way of trying to understand what is the individual performance of a player by sort of using these latent bases that the NMF is giving us. I'm not going to bore you through the details on how this is done. It's on the paper, but it's basically a probabilistic model where you need to infer the posterior distribution of a particular player to find sort of the regions where they're most effective. And again, not surprisingly, for example, Steph Curry is very effective in these areas, for example, right? So this sort of tries to understand the intricate details of a particular player's strengths. So this is one useful thing you can do with this. Are there any questions? All right. Now, I guess the most interesting thing you can use this tool for is quantifying defensive skills and sort of understanding how good a defender is. As Kostas mentioned, we have the adjusted plus-minus score that is trying to measure that, but it's not really enough because it might capture team sort of dynamics. And so here, what the authors do, this is sort of a follow-up of the previous paper that is slightly more heavy in the statistical side of things. What they try to do is they try to use the tracking data to, first of all, infer the locations of a particular defender. So they try to infer who is defending whom, and then given this particular offender's skills, they try to quantify the defender's efficiency. All right? And so in order to do that, there's a bunch of problems that need to be solved. And one of them is sort of trying to find who's defending whom. So you can do that by manually annotating the data, but it's a very painful thing. And so you could do that by sort of, sorry, the slides sort of go through the things that I talked. But you could manually annotate, but it's not a very efficient thing. And so what you would want to do is try to automatically infer who is defending whom. So the first step in this process is to find who's defending whom, who's guarding whom. And so here is how they do it, right? So basically this is a formula that says that the position of a player that is defending player K is dictated by this convex combination of different locations. So the location of the offender, so how far am I from the person who is offending, the location of the ball, and the hoop location. And so we have these parameters that we would like to basically infer using this model and the data. And so after we do that, we can then say that this person is guarding that person because they are the closest to this particular combination of locations, right? And in order to do that, we can also sort of make a further assumption that the defender's location with respect to when they're guarding player K, this is a lot of notation here, but just basically what it says is that my location as a defender with respect to player K is normally distributed around the mean position of the player K, right? So that's basically what this is trying to say. So we have to make this assumption in order to try to infer those parameters, all right? And this may or may not be a very realistic assumption, but we have to make some assumption, right? And this is a particularly useful one to make if we want to make the math, not too hard. So this is all what it is. So what we're going to do here is we want to try to infer those parameters to basically be able, for any particular pair of players, decide whether they're offender-defender pair. You can basically do the inference using expectation maximization. So we do like a two-step process where we first find the expected assignments of everything, and then we try to maximize the likelihood of the parameters. And we do that over and over again until it converges. And turns out that, I'm not sure if you can see that, but in the paper they discuss about how you try this in different configurations of data for different sort of time periods. Turns out that these numbers here are pretty sort of accurate in quantifying the location of a defender. So if you just hard code those numbers after computing them using EM, then you're pretty much able to find the defender's location. And sort of the two sort of take-home points is that the defender is closer to the offender when they're closer to the basket, and also that obviously the person who has the ball is defended more closely, right? But this is just a step in order to understand who's defending whom. And an example here is, in different configurations, this is the output of the algorithm after sort of doing these assignments where it says that, this guy is defending that guy and so on. And in cases where you have equal distance, you might have these two people defending another person. Now, why is this useful in and on itself? Besides the fact that we're trying to do that in order to quantify defensive skills, you can do cool stuff with that. For example, you can compute how much attention a particular player draws. And so basically by counting how many people on average this person is defended by, when they have the ball and when they don't have the ball. So you have these two distinctions. You can sort of say, these players have the most attention when they have the ball. And you see like MVP, great players are actually drawing more attention. And then when the player don't have the ball, we also have, let's say Steph Curry is obviously the most attention drawing player because he's very dangerous when he's being unguarded. So this again sort of follows intuition, but this is a neat way of computing how attention drawing with respect to defense a particular play is. Another thing you can quantify is a team as a whole, and you measure the defensive entropy, which is basically you measure how many times a particular player guards different people, basically how many different players a particular player guards, and this is giving you the entropy or the sort of the randomness of the defensive scheme, right? So if there's a man-to-man defense and a particular player only guards and always guards the same player, this is almost a deterministic defense, right? So if you measure the entropy and the entropy is higher than 0, it's as close to 1 as possible, then you can conclude that this particular team is using a sort of a more diverse defensive scheme. And so he's using double teams, is doing interesting things that are less predictable with respect to the defense. So the Miami Heat, for example, have probably not the highest entropy here. So this indicates switches in the defensive scheme and double teams and all sorts of things. So this is another thing that is really useful to do. But on our way to our final goal, we want to quantify defensive skills. And what we're going to base ourselves on is what I described to you in the previous sort of chapter, which was understanding shooting, latent shooting locations, right? So we have this tool that tells us where a player is most likely to shoot from and where they shoot from in general and so on. So there are patterns of shooting throughout the game. Now this can be used to understand, the skills of a particular defender who's guarding the player who's shooting from a particular location. So what we're going to do is we're going to use this to understand efficiency and frequency of a player shooting from a particular location, and then this is going to characterize the defender. All right, so if a player has low efficiency from shooting, let's say from here, this can be attributed in part to a really good defender. So this is the main idea. All right, so that's what we're trying to do here. Let's see. So what we're trying to, so there's a bunch of different bells and whistles to this model. For example, we want to sort of add some regularization, and we don't want to have all the players being sort of selected for all kinds of possessions, because this is going to be a sparse assignment of players to possessions. So the authors use sort of a regularization parameter. Think of sort of lasso-like regularization, where you sort of want a few of the players being assigned to a few possessions. So this is the so-called shrinkage parameter of the model, which we'll see later that it sort of helps get better accuracy, right? So now what we want to see is, are there different types of defenders, right? So first thing is we want to see whether they cluster well. And what the authors do is they take all these different bases of shooting locations, and they make a matrix of a basis per time spent guarding a particular player, all right? And so this, if you take this matrix, you take PCA, and you plot the two first principal components. This is the best way to project this data into the two-dimensional plane, right? And you see that there's clear groups of different types of defensive behavior. And so it's a good thing that the sort of defenders cluster well. And so this is sort of enforcing the intuition that, we should have the shrinkage parameter, all right? Now, if you try to do that for the offenders, turns out it's not working just as well. So the space does not appear to cluster as well as the defenders. But in order to find sort of a similarities between the offenders, what they do is they take the 10 nearest neighbors of the offenders using the weights of the non-negative matrix factorization, right? So these weights are basically like an embedding of a particular player to the sort of the latent shooting space. And so if you sort of take the 10 closest people to those people, then you'll find a network of similar players. And as you see here, it's this is the similarity network is not as clean cut as the defender network, but this also gives us, the coloring is different positions, and it's sort of more on par with the coloring. But this is to demonstrate sort of the similarity between offenders. But now let's cut to the chase, right? So there's two different things we want to quantify. We want to quantify the shot frequency and the shot efficiency. The shot frequency is basically a probabilistic model of how many times this particular player is going to take a shot from this particular latent location. And the efficiency is whether this particular shot is going to be successful or not. Now, this is a long formula that I'm going to slowly unpack for you. But basically, this is whether a shot happened from that particular location and what kind of shot that was. Was it a shot? Was it a layup? Was it, what type of shot that was? Now, this is depending on the propensity of the player. So how likely is the player to take a shot from that location? How good is the defender in blocking sort of shots from that location? And also, how much time is the defender guarding this particular player? So these factors contribute to sort of the frequency of a particular shot being taken from a particular location in the court. All right? So we can obviously use the data to infer the parameters, and we can do that. You can see the details on the paper. Now, the efficiency is a similarly packed formula, which is basically saying that, this is the probability of a shot being successful given that the shot was taken, and this is the distance between the two players. All right? This is the ability, the skill, how good the player is from shooting from that particular latent location, from one of the bases of the NMF. And this is the ability of the defender to block this particular shot. Again, obviously, if a shot is successful, is obviously depending on the ability of the person and the ability of the defender to suppress that shot, right? You see that if the defender is decreasingly able to repress that shot, then you'll see that the probability goes up. So this is these two models are going to help us quantify the defensive ability of a particular person, because we have all this data, we know whether a shot was successful or not, but we don't know, for example, the effectiveness of a particular defender in that location. So this is going to help us infer those things, right? And so we use all the data, and we can use, I think they use MCMC sampling in order to infer those parameters. But at the end of the day, what they have is a bunch of different numbers across the offensive court, defensive for the other team, that quantifies how efficient is a particular player in suppressing a particular shot. Now you'll see these are different versions of the model. As you see, no shrinkage means that we don't really take care of a few defenders sort of guarding a particular position. Here we don't really care about modeling the defensive skills of the defender. And here we don't really take into account the latent spatial information that the NMF gives us. You see that the model that has all those things obviously has better likelihood than the individual other models for different sort of things that it's trying to predict. So the shooter log likelihood, the basis of the location's likelihood, or the efficiency, for example, right? So in all these cases, all these different bells and whistles in the model, which make sense intuitively, actually indeed help have a better, more accurate model. Sorry. Now, to give you an idea, this is a nice visualization of two different players, Dwight Howard and Roy Hibbert. The way to read this is the following. So the smaller the dots are, the more efficient the player is to block that shot. Because this is quantifying the ability of the shooter, the efficiency of the shooter in the opposing team, the offending team, to score a shot from that location. So if the dot is smaller, this means that the defender was sort of more highly likely to block that shot. And this way you can sort of, for different latent locations on the court, quantify how effective a particular defender is. And this is sort of a more fine-grained quantification that goes beyond the plus or minus score that we saw in the previous part. But this is sort of a nice way to use spatial data rather, in order to quantify offensive and defensive skills on the half court. All right. So, are there any questions so far? Yes. The different quantiles on the distribution. Right. Now, switching gears. Here's another really sort of interesting problem and a cool application of things that you probably have heard a lot, especially at KDD, which is trying to identify different strategies that a team is using. And this is again on NBA data. And the idea here is a nice adaptation of topic modeling, as we'll see. And so this is going to help us understand, different sort of possession maps or sort of like sketches of how a team is utilizing their possession in different strategies. Is going to help us understand what sort of strategy leads to a shot and so on. And again, this is sort of roughly a 3-step procedure. So we have the raw data that says, this player has the ball, this player is here, and they do all sorts of things around the court. And so we need to segment those different possessions. Possession is basically if my team has the ball, then this is a possession and there's different movements around the court. So we need to segment those things into smaller actions, which are going to be sort of further, we're going to sort of cluster roughly those actions into action templates that, all these actions that lead from the from the baseline to the hoop is one single action. And then we're going to use possession modeling, which is sort of an extension of topic modeling, to understand different sort of frequently occurring patterns that constitute a strategy. All right, so let me just sort of go through all these different steps one by one, and hopefully it will make more sense in a few slides from now. Now, the authors use data that have around 200,000 possessions, and basically we have a trajectory for each particular player. We have a trajectory that is giving us the location over time. And what's happening here is we want to segment that into sort of more, we want to discretize it basically into different smaller movements. And the way this is done is here is, let's say, the actual locations on the court, and here's the velocity per time. So the idea is that you want to basically segment this trajectory in moments of sustained low velocity, right? So you basically have a threshold, and you say if the velocity of the player is below that threshold for X amount of seconds, or maybe less than seconds, then this we cut here, and this is one segment, all right? And so for this particular case, we have 7 different segments because we have all these dips here that fall under the threshold, and this is translated into different curves in the trajectory. All right, so this is the first step, to the pre-processing step, to make a longer trajectory in a possession a set of single actions. All right, now the second step is to cluster those actions into a sort of representative single action. And we could use all sorts of clustering here. What the authors use here that makes a lot of sense is those called Bezier curves, which are very, very popular in graphics. And you don't really need to understand the details right now, but basically it's a parameterized model that is expressed through those formulas, but it's basically given the trajectory, is fitting a curve that is as close to the trajectory as possible. And so we can use maximum likelihood estimation for that. And the results look something like that. So all the blue lines are the raw data, the raw actions that we segment. And the black line is the centroid, let's say, the Bezier curve, right? And so the authors take, remember about maybe 250 of those curves. Think about 250 clusters of different actions, right? Or different types of centroids of actions. So each one of those, so you see some of them are very clean cut, some of them are a little bit more rough, but hopefully when you take enough, then you are able to represent more fine-grained actions. And now comes the cool part. So basically we want to see what types of actions co-occur together and which action follows another action. So in the analogy here is if you have a set of documents, a corpus, then you want to basically find a distribution of the words over a particular document and the distribution of topics for a particular document, right? So here, instead of having a document being a mixture of topics and a topic being a distribution over the words, we have a possession, which is sort of the whole sort of set of actions of a particular offense, let's say, that is a mixture of strategies. So a strategy is a topic, and vice versa. And then sort of a strategy is distribution over those actions. So imagine those actions being our bag of words model, and strategy is a distribution over those actions, right? So this is a really nice connection between topic modeling and understanding, strategies in the MBA. You can use LDA for that. There's some details, one of them being that they focus on pairs of actions. So player 1 does this, player 2 does that at the same time. And so they're interested in sort of capturing this pair of movements. So for example, one player cuts inside the baseline, and then some player sort of maybe screens that player or screens the defender, right? So they are interested in capturing pairs of different actions. And so you can use LDA for that. LDA is probably the most popular topic modeling algorithm and topic model in itself. Here is a set of examples of different topics, which is basically, again, a topic is a distribution over the actions, right? So a strategy is a distribution over the actions. And you'll see here, for example, when this guy is going this way, this guy is cutting in from here. Or, this guy is going out, this guy is staying here, probably hopefully being free from the defender to take a shot. But these sort of pairs of actions that constitute different strategies shed light on different sort of offensive techniques that a team might use or a bunch of teams might use in their game. And this is a nice way to sort of try to index and search for different strategies that teams might be using. Now, obviously, not all different strategies use all possible different actions, right? So then, of all these 250 action sort of prototypes, only a few are used per strategy, which makes a lot of sense. Same way that not all documents use all the words available to us. And then another nice thing is that you can, because you have a distribution over this 250 dimensional space, which is again sort of an embedding, the topic model is sort of an embedding to the topic space, you can find similarities of different strategies. And you can sort of understand the similarities of each team's strategies, or whether there are similarities across teams. So for example, here is, let's say, this TSNE is a really, really nice algorithm for embedding high dimensional points, 250 dimensional points into the two-dimensional space. You can Google that. Is actually one of the state-of-the-art ways to do that. But here, basically what makes sense is that positions that are similar cluster together. And so here are the corner threes where one of the offender's cuts to the baseline cut, whereas here are different kinds of corner threes, and you see that they cluster in different locations. And so you have a very fine-grained understanding of different types of strategies that teams are using. Any questions so far? All right. Now, the last chapter of what I want to talk about is so-called ghosting in sports. Now, if you do social networks research, ghosting might mean something entirely different, but this is a different concept here. So ghosting was pioneered by the Raptors, Toronto Raptors. We're in Canada now, so it's a really cool idea. So here, hopefully you see the video. Ghosting is basically you try to model the location that a particular player should have been. What is the optimal location of a particular player at any given point in time, right? So you have the observations, spatiotemporal observations, and you say, you know what, I want to see, is this player doing what they're supposed to be doing, or are they doing something else? And obviously the ghost is the faintly looking dot here. Now, this is a really cool idea because it helps you sort of do what-if scenarios. The problem with that is that you need a lot of manual annotation to do that, right? Because you want to say, you know what, this player was here, whereas they're supposed to be here. And you want to do that for every sort of time slot of your data. And this is prohibitive. Now, there's a really cool paper at the MIT Sports Analytics Conference that is trying to use a data-driven approach to do that. And for a change, now we have soccer data. What the idea is here is, instead of having a golden standard of where this player is supposed to be, let's use data to see where, let's say, the average player in that position ought to be. Or let's use, let's say, Barcelona's data to see where this particular player in that position was on average for Barcelona against my team. And how would I improve my team by sort of seeing this insight, right? So train on particular data, game data, and use that as your ghost. This is basically the idea. And the way this is done is using what's called deep imitation learning. Again, I'm not going to go into the intimate details, but you can sort of skim through the paper to appreciate those. But basically the idea is it uses sort of a two-stage approach where it trains for a particular player and finds its ideal ghost. And it does that by using recurrent neural networks. And then there is a second stage where it trains for the team as a whole and has a feedback of the sort of the error incurred by a particular player's prediction model. Right? We're going to see a few more details on that. But again, the idea is use a recurrent neural network, which models sort of time dependencies, has a sort of a memory component, to learn what is the policy, that the next step of the time I'm going to use as a player, given the particular context and everything that I know about the state right now. Right? So this is the problem statement. Before doing that, it's important to sort of have a assignment of roles to each particular player. And the approach the authors use is, again, data-driven. And so instead of saying, what this guy is supposed to be, well, the goalkeeper doesn't change roles, but everybody else might, right? So this guy is supposed to be in that location, that position. But perhaps this person is effectively playing on a different position most of the time. And so what they do is they take the data and then they sort of try to fit a Gaussian distribution over a mixture of Gaussians over different positions, and they take the most likely one given the observed data for each particular player. Right? So then they use these role alignments to sort of assign to each player in the data. And after that, they sort of, for each player, they get a bunch of different features that capture the entire state of the game, and they feed that to a recurrent neural network, to LSTM. Now, this is what I basically said. You run the risk of having cascading, compounding prediction errors, and that's why you need to have a sort of a second layer that is a per team layer. So instead of just using a per player training, you want to have a per team network that is going to use a feedback of the errors of the particular player in order to counteract the compounding error that is happening per each player. Again, this is a lot of detail, but the idea is basically you need to use LSTM in a smarter way to learn this policy. I'm not going to go through that. It's okay. But you'll see here, well, probably you can't, but if I guess you probably can see the red stuff. So for most of the teams, this, the ghost is improving the sort of the percentages, the average goal percentage. That is a sort of a measure of success of a particular team. Although for some good teams, it doesn't really do much because it's training on the average performance, and some good teams are above average, right? So then this is basically good for teams that are lower than average and they're trying to improve themselves. But this is a really cool idea, because then as a coach, you might say, well, who do I want to compare my team against? I want to compare them against Barcelona or Manchester United. All right, let's train my LSTM using Barcelona's data, and let's see what would Messi do in that situation. And so this is a nice way of understanding, how your team would score against another team. Now, a big issue, as Costa has also highlighted, is how can you sort of quantify other intangible things like movement off the ball or even the ball movement, right? So maybe you could use similar ideas to quantify those intangibles by using lots and lots of data and use similar ideas as of ghosting, because a ghost is a pretty intangible thing on the court. So then this could be sort of inspiration for doing other things that could be very useful. And obviously, this requires a lot of training, it's a lot of heavy computation, but how could you use that, on a game day to sort of do something useful? Or maybe real time, how could you use that real time to say, to just yell to the defender, you should be there, not here, or something more sort of systematic to inform a strategy. All right, so that was my part, and I think that concludes the technical part of the tutorial. If you have any questions for that, I'd be happy to answer, but perhaps if you have any questions holistically for the tutorial, Kostas and I would be very happy to answer to you guys. So, questions? Yes?
When you show in the beginning, right there in the beginning.
The very beginning.
Yes.
Yes.
The matrix factorization.
Yes.
There was some of the bases that look very much the same. There is an identifiability problem there. I mean, you have to set the number of bases you mentioned.
Yes, that is a great point, actually. Let me put the slide. So you see those things here. Yeah. So yes, I mean, the NMF is usually not identifiable, right? Because you can find, in many nasty cases, you can find infinite solutions with the same sort of error, right? So there goes that. There are some results that talk about identifiability and uniqueness of the NMF under some conditions, but in order for those to be met, it might be hard for this kind of data. Now, you're absolutely right that perhaps those two are redundant, and this would actually, this was a particular choice of the authors of the paper. Perhaps you may want to sort of maybe get rid of those two, right? Just keep one, right? The other problem with NMF is that if I take k minus 1 components, it's not going to be guaranteed that there's going to be all but this one, let's say, right? So you don't have this sort of nice nestedness that the PCA does, because PCA has the orthogonality that guarantees that to you. And so just to summarize, yes, you're absolutely right. There's a lot of things that could be done to improve sort of identifiability and sort of redundancy. But this is nevertheless, it works well in quantifying different things. And so, yes, there might be some redundancy, but perhaps this doesn't hurt much in the end result. If you sort of want to understand this and purely for an interpretability sort of purpose, perhaps you would want to get rid of some of the redundant ones, if that makes sense.
It would be hard because the weights there are different, so you have to merge them.
You have to, would have to merge them. You would have to maybe do some, It is a hard problem to get absolutely right, but that is a great point actually. Yeah. Yes.
For this as well, for the tiling.
Yes.
What was the size of that tiling and how was it chosen?
Is it like, I think it's 48 by 50. So, however much the 250. So it's a discretized court per inch or something, per feet? Yeah, per foot. So you just take each tile is foot by foot.
1 foot by 1 foot.
Yeah.
Was that just shows around in the air, or just to make it 250?
Well, so that is another,
I think that because the dimensions of the court, the short one is 0, but from 0 to 50, and the half court 0 to 47, they just, so if you have a coordinate 42.8 and 38.1, it's 42.38. and it was just for simplicity.
Okay.
Again, you raise a, in spirit, you raise a similar issue here because this, if you make it too fine or too coarse, you might have different results. And I agree with you. At the end of the day, you want to make a sort of a decision that makes sense in terms of, 1 foot is realistically sort of the minimum that, you can sort of count a considerable amount of shots from, right? So that makes some sense. You may want to sort of try to experiment with different tilings, but again, I suppose in the long run it won't matter as long as you stay within a range that is reasonable. If you have like a millimeter tile, that would make 0 sense, right? So you want to sort of make a reasonable assumption, which that is a reasonable assumption. Thanks. Yes.
You showed a couple of plots of like certain defenders defending better areas on the court.
I did, yes.
I'm wondering if there's been any thought into how that might overlap with other defenders on the court, like building defensive units. Like for example, if one player is really good at defending the paint, for example, and then like your 5, and then your 4 is better at defending like the wings, and how that might intersect with the like optimal strategy utilized by like the offense. I wonder if like any thoughts gone into that, or if you see any like potential pitfalls with looking at like different strengths of defenders and putting them together.
That's a great point. As far as I know, I haven't seen anything like that. I'm not sure. Kostas can correct me if I'm wrong. And it's definitely worth trying. One pitfall that I may see, which doesn't mean you shouldn't try, is that this will increase the dimensionality. You take pairs of people, right? Or you want to take even the whole sort of configurations of people, right? So this will increase dimensionality and sparsity of what you observe, right? So this may be an issue, but then maybe with proper regularization, you would be able to tackle that. But this is a great idea, actually. Thanks. Anybody else? You're all hungry, ready for lunch? So, yes, please.
Is there any discussing with your NBA experts, and what's your opinion on your results? Because we can, based on your methods, we can get many different ranking results. So I'd like to know what's your opinion from the NBA experts.
My opinion on NBA as a sport? Or
NBA
sorry.
experts' opinion on your results.
NBA A plus.
Yeah.
On which results? This, I guess the results in the previous.
Just,
The ghosting.
Just like this ranking results.
Well, this is this is not a ranking. This is this results here.
Yeah.
So this, let me explain what this is. So this is for every player. This is how much they sort of participate in this latent component, which means that how much LeBron James shoot from this location as a percentage, or roughly sort of the intensity of LeBron James shooting from here. This is not a ranking. So this is just basically breaking down shooting behavior per location, latent location in the court. Similarly, as breaking down people who like different movies, right? So instead of court location, you can think of these are comedies, these are horror movies, and so LeBron likes comedies and Steph Curry likes horror movies, right? But instead of movies, you have locations in the court. Thank you. Yes.
I have a more general question, more related probably to the previous talk.
Yeah.
We talk about a team, like the Yankees are the Yankees, but that's not true, right? And the Yankees 20 years ago were a totally different team than the Yankees now. So when you showing some of the analyses on a team basis, is there a good sense of like how far back can you go before it really makes no more sense to be comparing Yankees to Yankees when they're really not the same thing?
Yeah, there is a lot of interest actually in that, and typically people tend to use the last 4 or 5 years because the sport changes extremely from year to year right now, right? So, for example, in basketball now you have this 3-point evolution. 10 years back, data completely different. Or in football, you have passing game mainly, passing and passing game. So definitely one of the issues that you need to use the very recent data. And one of the problems as you said, is how you compare players or teams from different era, and this is something actually that people have tried to do with statistical tests, like you find what was the norm during there, but it's very subjective, and still people haven't found a very good way to do that. But definitely, if you want to build game models, you need to use very recent data because the game changes.
Yeah, so I guess it depends on what exactly you're trying to
Yeah.
do.
The player also changes, right? The player evolves as well, right? So then even if you have the same players, you might want to take into account their evolution, right? So it's a hard problem. You could think of like using sort of embeddings per player.
Yeah, like treating more on a
Right.
basis than on a team basis.
Right. And then, but you have to have time evolving embeddings, right? To capture some of the time evolution, right? So that it's a really cool, interesting, open problem. Anybody else? You don't have to ask if you don't have anything. Just asking. All right. Well, thank you for coming here to service.